Hello everybody, so thank you for joining me in what is essentially the final video on integration in terms of the teaching part of it, because I don't think there's any way around it. In terms of mastering integration, we really need to do lots of it. So forgive the title, I've called this video Death by Integration, because it's just lots and lots of it, putting together the variety of skills you've now encountered and hopefully learnt through the duration of this chapter. So why do this video at all, you may be wondering? Well, I think it's important to emphasize just how crucial integration is as a topic for A-level, not just the breadth of it and therefore the importance in terms of marks, looking at it that way, but for going on in terms of any further study that relates to maths, whether it be a maths degree specifically or something like engineering, to really understand why and how integration works, and having an appreciation of a variety of techniques is absolutely crucial moving forward in anything extra to do with maths beyond A-level, or even if you're doing A-level maths, further maths rather I should say, this should be more beneficial in that regard too. So I'm going to get you started off with a warm-up as normal. So I've picked essentially 4 questions, which is one question yet 4. So it's the same integral, the integral of sine x cos x. The idea of this warm-up is to give you an idea of, with integration, there's often more than one possible way of tackling it, and that actually is fine, not something to be scared of once you get used to it and gain some mastery with integration itself. So try this integral using the different techniques. Do them as stated, don't just do it your own way. So press pause now, try these methods, and then question 4 wraps it up, where you should hopefully see and convince yourself that each, although looking different, is valid. Okay, so assuming you've had a go at those, let's see together the solutions to these warm-ups. So, question 1. So, part 1, integral of sine x cos x using a u sub, where u is sine x. So, that's no problem. So, if u is sine x, then what we can take here is du by dx. So, the derivative of sine is cos, so du by dx is cos. And so from that, we can rearrange to get dx as a subject. So dx in terms of du and cos x is just going to be du divided by cos x. So using this here, this is going to become, just get my pens in the right order. Using this substitution, u is sine x, so we just call that u. Cos x, I can leave as cos x for now, but then dx has been replaced with du over cos x. So in this case, dx is now this. And that's absolutely fine. In fact, that's good, because we can now cancel the cos x here and there. And so we're just simply integrating u with respect to u, which so therefore u du. Integrating u with respect to itself, of course, just half of what u is squared plus c, putting it back in its place because u is actually sine x. We've got half sine squared x plus c, where c is the arbitrary constant of integration. Emphasize arbitrary. I'll return to that point later on in the warm-ups. Warm-up question 2, same idea, but this time we're going to let u be cos x. So before I get these lines muddled, which I can often do when I drift or write too much or not straight enough, there we go. So this time, if u is cos x, du by dx will be different. Cos differentiates to negative sign. Again, we can rearrange this to get dx in terms of du. Dx is du all divided by minus sine x. So now, again, we can transform this integral. So sine x cos x, I've integrated it, and we've got this. Now we're going to integrate. I'll just give it a blue tinge this time. So on this occasion, we're letting u be cos x. So on this occasion, u is cos x, whereas before u was sine x. So we can transform this integral in a similar way. This time, I'll leave sine x as it's written. Now cos x is what we're saying u is, so I'm going to replace cos x with u, make the u sub, and dx, in our case, we've just seen that dx is du times negative sine x, so I'm going to put that as minus du all over sine x. So again, we can have some cancellations. So sine x on the bottom cancels sine x there. And so what we're going to have now is just the integral of a minus u du this time. So minus integral u du. But now our u was a different u, it's a cos. So that means it's the integral of u du, which of course is minus a half u squared it's going to go to, plus of course the arbitrary constant c. But of course, like I'm saying, this time our u is different. Now it's going to be minus a half of cos squared because u is cos. So our final step, we've integrated it. It seems to be fine. Yet we've got something that looks completely different this time. Regardless, that's question 1, part 1 done. So using this method of a u substitution using cos x, we've ended up with this here. Finally, let's just go again. This time using the trig identity that sine 2x is the same as 2 sine x cos x. Okay, so fairly easy to see. If I just divide both sides of this identity by 2, I can say that sine x cos x therefore has to be half of sine 2x. So I can make that switch now. So therefore, this here, this integral, because sine x cos x is actually only half of sine 2x, I can just rewrite this as half of sine 2x and leave the sine 2x on the inside because of course I need to integrate that. The constant I can take to the inside, the outside rather. So integrate that with respect to x, and this is fairly straightforward. It's just integrating a linear function of sine. So sine differentiates to cosine. That's how I remember it. Therefore, sine is going to actually integrate to negative cosine. So this one is going to just become a half of, we get negative cosine, but because we're integrating and there's a factor of 2, we need to divide by that factor of 2. So it's minus a half cosine of 2x, plus of course that constant of integration plus c. Half times half is a quarter, but one of these fractions is a negative, so to simplify fully, we get minus a quarter of cos 2x plus c. So how cool is that? We've done the same integral 3 times and got 3 different answers because of 3 different substitutions. When you get more confident of integration, you need to go from seeing this as being scary, as unfamiliar, ambiguous, which one's the correct one, to being comfortable thinking sometimes of maths, integration can be like an art form. There could be different expressions of the same integral. And this is one of these examples here. Albeit it looks simple from the outside, just integral of sine and cos, it makes a very powerful point, or at least I hope it's doing. Right, let's have a look now at warm-up question 2. So again, keeping with exactly the same theme, exactly the same integral, we're going to integrate sine x cos x again now, but only using integration by parts. This time though, we're going to set sine x as u, so we're going to be differentiating sine x, and cos x we set as v dashed, so in other words we're going to be integrating cosine x. Now, whether you're watching this video using whatever method you do for integration by parts, I'm going to use the DI method, which I basically stole from Black Pen, Red Pen. It's great, check it out there first. It's not my method, but I think this is much easier. So using the DI method for how to integrate by parts, here's what we're going to do. So the function we're going to differentiate, we put in the D column. So that's going to be sine x, and whoops, And the function we're going to integrate, we put in the I column, as in I for integrate. So sin x is the d, I is cos x. Sin x differentiates to cos x. By the way, if you're wondering what on earth this table's about, if I've not given you enough explanation, because I've not, I have made a previous video which details this quite fully. If you scroll back through the playlist, you should find it there, or in your notes if I teach you. Anyhow, so sin x differentiates to cosine x, and then cosine integrates to positive sin x. So what we need to spot with this DI method is we stop when we get to a multiple of the integral itself. And so what I'm going to do here, I'm just going to call the integral, let the integral of sin x cosine x dx, let's just call that I for integral. Then, using this integration by parts technique, we integrate the diagonal columns. So we take the diagonal products, I mean to say, I'll get that in a red colour in fact, and we stop with these diagonals when we hit a line where we can integrate the product of that. But if you have a look at the product of minus cos x sin x, that essentially is going to be some multiple of the integral itself. So what we're saying here is we're going to get a duplication of the integral. So let's just see what happens here. So we stop when we get a duplication. That's going to be the case. So we can actually stop, which you're going to see in a second, just after the second line. So this integral, as I say, we take the product of the diagonals, multiply, so we've got sin x times sin x, so sin squared x. Then we integrate the product of this final row, so it's minus cosine x times sin x, so it's minus the integral of sin x cos x dx. So that's why we're stopping at this line, because we've got some multiple now. So we can actually just make this substitution. So it's almost algebra wrapped up in integration. So because this is I can rewrite this now as just the integral, is sin squared x minus itself, because this here is I. So rearrange, add I to both sides, so 2 lots of I equals sin squared x. This is slightly lazy algebra because dividing now by 2 should just say be I equals half sin squared x. So if it's purely algebraic, that's what we do. But we just need to remember, because it is actually representing an integral, that our final version of I needs to include that pesky arbitrary constant of integration, the plus c. So the integral is a half sin squared x plus c. And we've seen that form before in question 1, when we used the u substitution to arrive at this. So the integral, this is half sin squared x plus c. Let's try question 3. So question 3, again integration by parts, but this time the function to be integrated is going to be sin x, and we're going to be differentiating cosine x. So again, using the same DI method in the table, I'm going to be differentiating cosine x. Differentiate cosine becomes negative sin x. And over here, we're going to be integrating sin x, and sine integrates to negative cosine. Again, like I've said before, the DI method, we take the product of the diagonals of rows, and we stop till we get to an arrowhead which lands on a row where we could integrate this product here. Now, if we notice about integrating this product, we're going to get some multiple of sin x cosine x, which is some multiple of the integral itself. when that happens, that's a clue to stop. So we're going to stop here. Whoops. Just meant that as a normal line, not one with an arrowhead. Not that it really matters. Maybe I'm being slightly too picky. Anyhow, so very similar to warm-up question 2. This time I'm just going to let the integral, again, be called I. So the integral is sine x cos x with respect to x. And from here, using this DI method, we can see that the integral is its diagonal product. So cos x times minus cos x, that's minus cos squared x. Then integrating this product, minus times a minus is a plus, times another minus reverts to negative. So again, it's a negative overall product of sine x cosine x with respect to x. But just like in warm-up question 2, this here is what I is. So then, making this explicit, we've got I is minus cosine squared x minus its very self. Rearranged by adding I to both sides, we see that 2i must be negative cosine squared x. Finally dividing by 2 and realise it's slightly lazy algebra this. We need to actually integrate and therefore factor in the constant of integration, the c. Therefore the integral, which I'll just spell out loud for the purists, there's no harm in doing this. That's what the integral actually was. It's minus 1/2, after dividing by 2 on both sides, of course, cos squared of x plus c. And we've seen that form before. Let's piece this together now. So let's go and have a look at question 4. So question 4, we're going to show now using the suitable trig identities and manipulations that each result from questions 1 to 3 can be written in this form here. You can all get it into the same form, so it's arbitrary, but let's show that they can all be written as half sine squared x plus some c, where c is an arbitrary constant. So because I want to arrive at this result for the other 2 forms we saw, I'm going to start off with their resulting integrals, the integration after it's being done, I mean, as the arbitrary constants being a d and an e. So we're going to start with d's and e's, and then manipulate those to show that we can re-arrive back at the same form here. So what 2 other forms were there? Well, if you can't remember, here they are. So the other 2 results we had was minus 1/2 cos squared x plus d. So how is that going to look like this? That's quite a simple one. And this result here, how am I going to show that this is the same as that? Again, slightly harder, but you'll see it's not so bad. So I'm going to start here with minus 1/2 cos squared x plus d. So again, if I just call this the integral. So the integral is that. So cos squared x, I want it in terms of sine squared. We should know that sine squared plus cos squared equals 1. Therefore, cos squared I can rewrite as 1 minus sine squared plus d. So just to emphasize that, all I've done here is said cos squared is the same as 1 minus sine squared. I can now expand all this out. So minus 1/2 times 1 is minus 1/2. Minus 1/2 times minus sine squared is positive 1/2 sine squared x plus d. And now d is a constant and minus 1/2 is just a constant. So I can group these together and these can be what we called c here. So final step, I'm just going to say rewrite this as 1/2 sine squared x plus c. Then to emphasize what we've done, where c in this case is minus 1/2 plus the initial arbitrary constant which we had was d. So all I've done there is said I'm going to take this constant plus d, let's just call that a new letter, c. So it works exactly the same. So what we had here, we've re-arrived at over here too. This time we need to go a different route. So, oh, that's rather annoying, I just noticed now I didn't include the integral signs. Apologies, everybody, but those should have integral signs on there. My bad. Okay. This time, cos 2x. We need to remember the double angle formula for cos 2x. So cos 2x, generally speaking, is always cos squared x minus sine squared x. That's strictly speaking an identity, so I should say there a 3-barred equals. But essentially, from here, we can make a start. And so from here, the integral, which we had was negative a quarter cos 2x plus e. I'm just writing it out again for now. That's the same as minus a quarter, but cos 2x I can replace with cos squared minus sine squared. Plus e. Now I want it all in terms of sine squared. Sine squared's fine, it's already in terms of sine squared. Cos squared is, of course, 1 minus sine squared. So 1 minus sine squared minus another sine squared is 1 minus 2 sine squared of x plus e. And at this stage, I can now expand out as well. So now I'm going to get minus a quarter times 1 is minus a quarter. Minus a quarter times minus 2 is positive 2 quarters, which is positive a half. I've got half sine squared x plus e. And now again, similar to what we did earlier, I've got half sine squared x, and some constant e minus a quarter will still be another constant. It'll just be a constant which is 0.25 less than what e was. So I can just group e and minus a quarter together, and that can be our c, if you like. So this now equals a half sine squared x plus c as required. Exactly the same form, so we're done. But again, I'll just state clearly where c is simply negative a quarter plus e. So we've shown the results to be clear and consistent and each mutually valid. So this brings us on to the main point now. After doing integration for what must feel like several months of your life, I apologise slightly for the title, it's just to do with how severe I think students like yourselves will find it. It's hard work, and this is going to be hard work I'm asking you to do. It's, yeah, death by integration. So we've just seen how one integral, the integral of sine x cos x, can be solved in a variety of different approaches. So in what methods can be used to integrate and why is key to efficiency and mastering the topic of integration for A level. Efficiency there, what I mean is, the sooner you spot what to do, it just takes the mystique and stress out of it. You can get straight into solving the question rather than just faffing around not knowing where to start. As the warm-up questions showed, there can at times be an overlap of approaches, and as you transition towards mastery, this seeming ambiguity will begin to feel more like freedom, where you're able to choose the easiest method for yourself. Easiest method in your own opinion. Integration can be rather subjective, and each teacher will tend to teach it slightly different to others. Not to knock anyone else's methods, I'm sure there's lots of different methods for teaching different things. There of course are, but because integration is more like an art form, it can be taught in different ways, which again can make it seem slightly more confusing. Going back full circle now, the title, that's why you need to do lots of it. Do it as much as you possibly can. The fact we can sometimes have multiple approaches, why is that? It's a consequence of some integral types falling across multiple categories, of course. So below detail some general tips and strategies, followed by a flowchart for reference. Now this asterisk is just to let you know, the flowchart I'm going to show you is not including the trapezium rule or the method of separation of variables. So if to include all those would just to make something huge be just enormous. So the video is already going to be long enough, and also, well, I didn't include the trapezium rule because that's rather standalone and fairly, touch wood, obvious to spot, but it's not like a standard integration question. And questions where you need to separate the variables, it's an integral question where it almost looks like a differential equation. It'll have a dy by dx or a dx by d theta or something in it. So they're easier to spot. So anyway, these tips and strategies. So general advice and tips. This is not exhaustive. Okay, this is not exhaustive, so bear this in mind. There's no substitute for practice. But one tip is focus on the trig terms first. Anything trigonometric, like fractions, can be simplified. It'll be expressed or can be expressible in a simpler form. So can the triggy stuff be simplified? Is there some identity we can use in the formula book to make it more understandable? Is one of the trig terms the derivative of the other, multiplied by some constant perhaps? If so, we might be able to use the reverse chain rule or a u sub on it. So the trig stuff can be really off-putting because students tend to find it really hard. So first and foremost, can anything, the triggy stuff, is there any simpler way of expressing that? So what underpins good integration is good mastery of trigonometry. So that might be good news or bad news, as it may be. Second point I'd make is, with algebraic fractions, make sure if you can they're fully factorised, especially the denominators. Then, or even before, just think to yourself, is the derivative of a denominator some multiple of the numerator? By that, I mean to say, sorry, some multiple of the numerator. Okay, not the derivative of a numerator, that's me making a typo. My bad, I'm going to just plaster over it here. I hope you'll forgive this fudge. So, after saying that, could we use partial fractions on it? Often you'll find you can. And the final thing, integration by parts, essentially looking for it as a product of two things, where we know how to differentiate one of those things and integrate the other. So I do remember, sorry, last thing to say before we get started off on some of these on our own, never forget that fractions can be expressed as products. So sometimes it might be an integration by parts question in disguise, or something like this. So sin x cos squared x, you might be drawing a blank, but perhaps if you write it as sin x sec squared x, that might be a more useful form. So what's this flowchart all about? Well, here I go. Just give me a moment or two to try to explain it, but you're best off just trying to digest it on your own. So, big breath. Yes. Wow. I do not ever expect anyone to memorize this. So why make it? The idea being, you can always start at a foundation, okay? It's never a case of where do I even begin? I want to just dispel that myth visually, if nothing else. You can always know how to begin. First step. Again, in exams, it's surprising how people can panic. Does it actually suggest a method? Sometimes it will. If it does suggest a method, without stating the obvious, use that method. That's actually contrary to what I just said. I mean, stating the obvious, yes, because I have stated the obvious, but use that method. Don't do anything the examiner is telling you not to do. At the very best, it's a waste of time. At the very worst, it's a waste of an exam. If a question doesn't suggest a method, almost always it doesn't, what I'd suggest to look for next is it a fraction? If it is, again, check the derivative of a denominator. Could it be a u sub or reverse chain rule? Or if not, is it a polynomial numerator and a singleton denominator? For example, something like 6x divided by x to the power 4. If so, you can split that into separate fractions, make it simpler, then integrate separately. Or maybe not. If it's still a fraction, but the denominator is a polynomial and it can be factorized, or that might be a partial fraction job. If not, this is where I'd consider that tip I made earlier, consider rewriting the fraction as a product. So rather than tan x over cos x, write it as a product. If you've not considered rewriting that, probably integration by parts. And if not, some troubleshooting down here I'm going to mention in a second. So that's if it's a fraction. There's loads to consider if it's just a fraction or not. If it's not a fraction and it's a product, or something like a product, be checking, is it one of these standard forms? Is it a standard integral where you're integrating a linear function of something standard? Is it a reverse chain rule where I would suggest to use a u substitution, where u is the inner function, if you like? If not, then chances are it's going to be integration by parts, where you've got two things and you know how to integrate one and differentiate the other. And always prioritize what to put in the D column when I use the DI method. Check out another video on that if you've not seen it. Prioritize what to differentiate, in other words, your U, using the standard method, according to late. So logs first, then algebraic, then trigonometric, and the last thing you want to try and put in the D column would be something exponential. There will be integrals, no doubt, for you doing past papers or in class or on your own, who knows, where you do get stuck. You think, I've tried everything, what's gone wrong? So if this is the case, I've put a troubleshooting section down here. If you get to this stage, double check and rethink any useful trig identities. That can be a key one. If it's a trig thing, it tends to be really hard for trig in A level. Double check the trigonometry if it's a trig integral. If not, a U substitution. Can it be a different possible U sub? Could any product or group be written in terms of another? So for example, if it's integration by parts, could be if it's something like x squared multiplied by, then in brackets, x minus 2 squared, because x can be written in terms of x minus 2 and vice versa. So if it's an algebraic product, it may well be a U sub is the thing to try. Now, the last resort, this is really above and beyond the scope of the standard A-level course. This is more going into further maths, but if you come across something where it's an x squared plus some number squared, this is really last ditch. I am not recommending this, I say again. You could try subbing x equals some a tan theta. Or if you see some constant squared minus x squared, that or that square rooted, you could try x being a cos theta or x being a sine theta. Again, if you're sure you've tried this, even the last resort, don't overly stress it. It's never life or death. No pun intended, it's just a bad title of the video, Death by Integration. Anyway, I digress. Leave a question and look again later at it, or seek help from your teacher. So don't give up like forever, but do, just leave it for now and return to it later on. Only give up, I'd say, if your teacher or if everyone is saying, yeah, Mr. Bailey said ignore that one. But generally, try to understand and attempt every single question. So, in terms of this trigonometry, it'd be well recommended to know that this here is essentially in the formula book. This is my adaptation of what the formula book gives you for derivatives and for integrals, and because differentiation and integration are inverses, you can consider them with a bit of thinking as going all one way. So I wrote all of the trig integrals and derivatives as integrals. So integrating from left to right. So sec squared x integrates to this, and so on and so on. This is given to you. It's great if you know some of these off by heart, but all these are essentially given to you in the formula book. So if it's a trig integral and you're not sure what to do, double check this. Okay, having said that, now it's over to you to get stuck in. So I'm going to underline the two main tasks for you to do it. So the student activity. Part one of it, you need to be classifying each of the below 28, yes there's a lot of them, indefinite integrals. I kept them all indefinite to make it slightly simpler. 28 definite ones would take forever. So you need to classify these integrals into the correct rows of the below table, which I'll show in just a moment. Some integrals can be attempted using a variety of different methods, like the warm-up showed you, so don't fear if you're not sure which method to choose. There may be more than one choice. So what you could do here in the table, I'll show in a second, some integrals could be classified into a variety of different strategies. So you can put some integrals into different rows for the different strategies each row represents. Here are the integrals. So yeah, quite a lot. I've kept them just purely maths. I've not given you any written questions. So these are like the raw tools to practice on. The table to classify them into is this one here. And as I've said before, integrations are a very personal sort of thing to teach. Different teachers will have different sort of ideas and ways perhaps of classifying them. This is my particular way. in my head how they work. So for each one, put a tick into which type the integral is. So for example, integral A, if you think it's a partial fraction, put A here. So that's for you to do now. So part one is just to simply classify the integrals. So I'm going to show you now the answers, the solutions to how I would personally classify these integrals. Step two, part two, is to actually integrate them. So part one, spoiler alert, that's how I'd classify them. Part two, having filled in the below table like we just have, use the corresponding methods to evaluate each integral. Check your answers using the short solutions first. If this is still unclear, check the handwritten solutions. If handwritten solutions still aren't helping too much, feel free to check the video solutions for each integral, and if you're still not sure, please do check in with your teacher or at a lunchtime help session, for example. Okay, so let's now get integrating. I'm not going to do them in the order in the table, I'm going to do them alphabetically. So let's start with integral A. Okay, the first integral, integral A. So sin x plus cos x all squared with respect to x. I think this is going to be very obviously one where we're going to need a trig identity. So although I could get the flowchart out and show you, I think it's so obvious it's going to involve trig, it's not even worth really using the flowchart. So anyway, if I just take this and expand out, what we're going to get here is sine squared x, because obviously sine x all squared is sine squared. Then we're going to get two lots of the product, so we're going to get two lots of sine x cosine x. And finally, we're going to get cos squared x. All of that with respect to dx. So obviously, we can, or we should know, that sine squared plus cos squared is the same as 1. So we can simplify this. So I'm going to get the integral of 1 plus 2 lots of sine x cos x dx. However, we can now use a trig identity. So I'm going to tick here for trig identity, and I'm going to put this in a red box. So next, we can also use something else. So 2 lots of sine x cosine x, we need to recall this is a double angle formula. So obviously those become 1, but 2 lots of sine x cos x, that's the same thing as sine of 2x, okay? And so even though we could integrate the 2 sine x cos x part, like we saw with the warm-up questions, we could even use integration by parts or a u-sub. In my mind, and this is why I'm going to do it this one way, a substitution of 2 sine x cos x for sine 2x is simplest. If you want to try it a different way, by all means, that's absolutely fine. Just double check using Desmos or asking your teacher. And so that's going to become just sine 2x dx. And finally, we can actually just integrate this, because sine 2x is essentially just integrating of the form f of ax plus b. So now we can just integrate as standard, really. So 1 obviously integrates just x. Sine, I always think, differentiates to cosine. Therefore, sine integrates to negative cosine, but because it's sine of 2x, we need to divide by that 2. So we're going to get minus a half of cos 2x. Then, of course, you need to remember that pesky concept of integration plus c at the end. And so that's the first one done. And so for that reason, I'm going to put there, it's using a trig identity. So just box this off here. And that's the first integral done. So our answer is x minus a half cos 2x plus c. Integral b, x squared cos x dx. So how are we going to tackle this one? So this time I'm going to show you actually the flowchart. So I've got x squared multiplied by cos x, so it's a product. So if we go to the flowchart here, start, does the question suggest a method? No, it doesn't, so go down this route. It's not a fraction, so I'm looking already in this form here. So is it an integral where it's reverse chain rule, so we're integrating a function inside an inner function, or do we have it where we've got a product and one of the products looks like the derivative of the inner function f of x? Well, no, not really, because if I just scroll back up and show you, cos x, the derivative of that looks nothing like x squared, and if we differentiate x squared, it looks nothing like cos x. So no, it's not a u sub of that type. So we go no. Is it integration by parts? So we can use integration by parts when it's a product, which is what we've got here. It is a product of two things. And as well, we can use integration by parts when we know how to differentiate one of the terms a few times. We can differentiate x squared, for example. And if we know how to integrate the other term a few times, which we can do, we know how to integrate cosine x. So therefore, we're going to use integration by parts. So we're using that one because it's a product, and we can differentiate one easily, integrate the other easily. So I'm going to put here it's integration by parts. So the way I suggest to do this is to use the DI method, using this table or a construction similar to this. We prioritize D, the one which is to be differentiated, according to the acronym LATE or LIAT, if you want to do inverse trig as well. So L stands for log, there's nothing logarithmic. A stands for algebraic, which we do have, and A comes before T for trigonometric. So A takes precedence. So algebraic, the algebraic term is x squared, I put in the D column. Therefore, in the I column, we put the other thing, which is cos x. For D, we differentiate down. I, we integrate when we go downwards. So cos actually integrates to positive sine x. And we stop when we get to a row which we can integrate. Can we integrate 2x times sine x? Well, it's not trivial, so we need to differentiate again and integrate again. Differentiate 2x gives us 2. If we integrate sine, we get negative cosine. This line, could we integrate minus 2 lots of cos x? Yes, we can. So we stop when we get to a line we can integrate, so we stop here. And as well as that, we take the diagonal products of these rows, stopping when we get to an arrow which touches our final line. This arrow here touches this final line, so we stop. And so it's that product, and then this final integral. So therefore, from here, we can see we're going to have x squared, in fact I'll put it here as well, x squared sine x, and then this product, be careful, this is a negative now, so it's minus 2x multiplied by minus cos x, minus multiplied by minus, of course, is a plus, and we get plus 2x cos x. Then finally this integral. So positive 2 multiplied by minus cos is going to be minus 2 lots of cos x, and I can take outside the integral that constant 2, to get minus 2 lots of the integral of cos x dx. And so piecing this together now, I've got x squared sine x, obviously, plus the 2x cos x. Now here, cos actually integrates to positive sine, and so minus 2 lots of the integral of cos x just becomes minus 2 lots of sine x. And of course, you need to remember that constant of integration, which in our case almost always we call positive c. And so that's integral b complete. Integral c, again, just by looking at it, it's clearly triggy. It's nothing but trig, in fact. So sine squared x, cos squared x dx. So the main challenge is, once you've got to establish, I think it's almost too obvious to say, it's going to be a trig identity of some sort. But that isn't the end of a problem. It's knowing which one to use. And if you're not careful and haven't had enough practice, you can easily get yourself into a mess. A common mistake here would be to think, oh, well, sine squared is 1 minus cos squared, or cos squared is 1 minus sine squared, and then to get it all in terms of a sine squared or a cos squared. But if you were to do that, you'd end up with sine to the power 4x or a cos to the power 4x, which isn't straightforward at all, unless you want to go into more identities and double angles. So that isn't the best one to use. The best thing to consider, in my opinion, is the double angle formula for cos2 theta. So just over here, I'm going to put this in a little thought bubble because we're going to use this in a second. So we need to remember, ideally, and this essentially is in the formula book, cos2 theta is one and the same as cos squared theta minus sine squared theta. Okay? And then we can go on and adapt this in a second. But from here, I'll show I'm going with this in a moment, but we're going to be using this in a second. So if I just take this here, the best thing to notice would be this is sine x cos x all squared. So if I just put this all into a bracket and say it's sine x cos x all squared with respect to x, then hopefully you'll spot that this is obviously going to be the same as sine x cos x is the same as half of sine 2x. So I'll explain why that is as well. Okay, so if I make a little box here, just so it's clear in terms of where I'm going with the explanations of all these things. So what I've used here is the identity that sine 2x is the same as 2 sine x cos x. So this is the identity I'm using so far, which I'll just highlight so you can see where I'm going. I don't mean to go into over detail, but again, with integration being such a big thing, I just want to try and make it as clear as I can without trying to obviously patronize. So sine x cos x is the same as half sine 2x all squared. So of course we can expand this out. So a half times a half gives us a quarter. I'll put the to the outside of the integral. And on the inside I'm going to have sine squared of 2x dx. Now at this point we're going to get rid of the sine squared using this double angle formula. So again, what I'm going to do is just put this into a little box here. Not like that, you silly sausage. Let me think what I'm trying to do. Line color, yeah. Never mind. Losing brain cells as we speak. I'll just box this off manually. But essentially, yes, sine squared 2x needs to go. So leave a quarter as is. I could do with having this sine squared in terms of just a single sine or a single cos. So I can get rid of the cos squared here by rewriting it as 1 minus sine squared theta. Leave minus sine squared as it is. So therefore cos of 2 theta is the same as 1 minus 2 lots of sine squared theta. So I can rearrange this in terms of sine squared. So therefore 1 sine squared of theta, rearranging, will be 1 minus cos of 2 theta, all divided by 2. And so we're going to make this switch here for sine squared. Going to replace it with this here. But of course, not talking in terms of theta. In our case, we're talking in terms of a 2x. And so if I say theta is 2x, then 2 theta will become 4x. And so making this identity switch, we've got 1 minus cos 2 theta. Silly, silly me. So if you're wondering why I'm being so prone to mistakes, it's in my mind it's early in the morning. That becomes cos 4x, my bad, all over 2, all with respect to x. So this is the second identity we're using. The first one was the sine 2x is 2 sine x cos x here, and now we're switching out the sine 2x with this. And then we can proceed as normal. Because the denominators are half, I'm going to obviously factorize out this half because I can. So a quarter, then times that by another half. Let's put the 8th to the outside. And then I can just integrate the numerator. So 1 integrates to x. Cos integrates to positive sine. So because it's a minus cos, it'll go to a minus sine. It's 4x, so it stays as 4x. But because it's a 4x, you need to divide by that 4. Then, of course, the old constant of integration. This, of course, can be neatened up. So expanding out by this 1/8 gives us 1/8 of an x. 1/8 times a quarter is a 32nd, and the minus, of course, sine 4x plus c. And that's integral c complete. So again, just be careful with which particular trig identities you're wanting to choose. Integral d. This time we're told it's a u sub. We're told to use the sub that u is sine x. So again, we're just going to follow the instructions. So again, method provided, it's a sub. So I'm going to tick this box. So let's just write out what we have. So if u is sine x, then we can differentiate u with respect to x. So differentiate u with respect to x, differentiate sine x with respect to x just gives us, of course, positive cos x. So from that, we can see that dx is equivalent to du divided by cos x. Like so. So what we can do here is then just substitute this into this integral. So if integral d, so it's 1 plus sine x all over cos x with respect to x. And then, of course, we can do some alterations with what we have here. So 1 plus sine x, of course, is going to become just 1 plus u. So we can write this down already. So we get 1 plus u. Cos x I'm going to leave as it is. And then dx, of course, is the same as du all over cos x. So all we've done here is replaced the sine x with u, because u is sine x. And again, we said that dx is one of the same thing as du over cos x. So far I've just made those two switches. Of course, cos x multiplied by another 1 over cos x is going to be 1 over cos squared x. So that's going to be our next step. And at this stage, it might seem a bit confusing, like where's this going to end up going? But just bear with. So I've got 1 plus u all over cos squared of x with respect to u. And of course, that's a problem as it stands, because the integral is in terms of different things. It all needs to be in terms of u, because integrating with respect to u, so this cos squared x at the bottom, is a problem. However, if u is sine squared x, then of course you just need to remember from this that therefore, using the identity that cos squared plus sine squared is 1, we can say that cos squared of x, which of course is going to be 1 minus sine squared of x, that's the same as 1 minus u squared. So I'm just going to put this into a thought bubble because we can use this as well. So essentially what I'm saying here is the cos squared of x we can now switch out with a 1 minus u squared. So let's do that as our next step. So I've got 1 plus u all over cos squared of x, which is 1 minus u squared. All this, of course, with respect to u, like I say. So now what I'm going to suggest we do, this is difference of two squares, so I'm hoping you'd spot this yourself. It's almost too tempting to want to factorise this, and factorising is the right move. So we go 1 plus u, then all over 1 plus u, brackets 1 minus u, all with respect to u. Now, if you're being particularly brainless, or like me, if you're tired and need a coffee, it might be tempting to just think, oh, partial fractions this out, but please just have a look. Don't ever ignore the obvious. There's a 1 plus u on the top and a 1 plus u on the bottom, so we can divide through by this common factor. So we do that. So then what we're going to have is, I've got 1 on the top now, and on the bottom 1 minus u du. Now, if I were to differentiate minus u, I get minus 1, which is the same as the numerator, just different by a constant of minus 1. So this goes back to essentially integrating in terms of natural logs. If the numerator is the derivative of the denominator multiplied by some constant, in this case by minus 1, then we can write the integral in terms of the natural logarithm of the denominator. So this is going to become minus ln of 1 minus u plus c. It's a minus because the derivative of 1 minus u would be minus 1, so I need to put the minus there to balance that constant. Of course, we can't leave it like this because we need it in terms of the original variable, which of course was the x. U, of course, was sine x, so I put this back into my final answer. My final answer now is minus ln 1 minus sine x, all modded, plus c. And because sine x is never going to exceed 1, we don't really need these mod signs in, but when it's ln, I think including the mod signs is safer because it'll always work. So that's integral d complete. Integral e, again, is trigonometric. One of the reasons I've picked lots of trig type integrals is because there's just so much trig in the course, let alone just the integration. But anyway, cot squared x. So clearly it's going to have to be some sort of identity we're going to need to use. If ever you're integrating trig, always be checking the formula book first. Is cot squared x one we're given? Well, let's have a look. So this is essentially what you'll find in your formula book. What I've got here is from the notes I made, which you should have in your handouts. This is a mixture essentially of the differentiation and integration results which you're given in the formula book. But for the sake of simplicity, I've just categorized them all as integrals. So anyhow, so we've got cot squared x, which is trying to integrate. I've got cot, but that's not cot squared. I've got sec x in two different ways. Right, so there's nothing that we can integrate cot squared with. So that proves, like I've said, we need some identity. So let's start from basics. What does cot mean? Well, cot is 1 over tan. Tan is sine over cos, so cot is going to be cos over sine. Square it means this integral is just cos squared all over sine squared. Now, just by writing it like this, that should hopefully jog our memories that we can write cos squared in terms of sine squared or sine squared in terms of cos squared. It's normally easier to keep the denominator simpler, so I'm going to make the switch on the numerator. So I'm going to just rewrite cos squared as 1 minus sine squared. All over, of course, still sine squared. And that's with respect to x. I can now partition this fraction here, so I can write it as 1 all over sine squared minus sine squared over sine squared. And this last bit, of course, will just become 1. So 1 over sine squared, that's just the same as cosec squared. So that's cosec squared x, and then that becomes minus 1. So at this stage, we can again recheck on the formula book if we want to. So cosec squared x, is that a standard result? So again, just scroll down. And what do we have here? Yes, it is. So cosec squared integrates to negative cot. The constant here is just 1, so it just goes to minus cot x. So cosec squared goes to minus cot x. Integrate minus 1, of course, will just give us minus x. And then, of course, a constant of integration, lest we forget, plus c. Finish it all off, underline, and we're good. And that's integral e complete. Integral f, 2x squared sine 2x dx. So this is a product. So let's just think about this. So if I go here with a sort of flowchart, there's no method given, so go down here. Is it a fraction? No, it's not. So go down this path here. Is the integral of the form k f of ax plus b some inner function where the derivative appears of it? Well, does it? No, derivative of sine 2x is nothing like 2x squared. If you differentiate 2x squared, it's not a trig function, so it's not this either, so go no again. Could it be integration by parts? Integration by parts is when you've got a product of two things. Well, we have essentially. If you look here, we've got 2x squared multiplied by sine 2x, so that does work. And we can use integration by parts when we can differentiate one thing a few times and integrate the other. If we know how to do that, we can use integration by parts. Well, I can certainly differentiate 2x squared, that's very easy. And sine 2x, because it's a linear function of x, that's going to integrate to cos and then back to sine and so on and so on. And so this ticks all the boxes for us being able to use integration by parts. So for that reason, it's integration by parts. So now we know what we're doing, let's do it. So with integration by parts, I would go for the DI method, where D is what we're going to differentiate, and we prioritize for the D column according to the acronym LATE, where L is log, A is algebraic. A for algebraic comes before T for trigonometric. So because A comes first, we're going to prioritize for 2x squared, this algebraic part, for the D column. So if 2x squared is the D column, the other bit, sine 2x, is what we're going to be integrating. So differentiate going down, 2x squared differentiates to 4x, 4x differentiates to 4, 4 of course, if you wanted to, go down to 0. Integrating sine, well, sine actually integrates to negative cos, but because of this constant 2, we need to divide by that. So integrating sine 2x gives negative 1/2 cos 2x. With the DI method, we keep going until we get to a row we could integrate the product of. If I take the product of minus 4x and minus 1/2 cos 2x, I've still got an awkward product, so I need to integrate again. Cos integrates to positive sine 2x. So because it's a minus already, it's going to stay as a minus. But again, because of that 2 again, we divide by another 2. So 1/2 of 1/2 is 1/4. And of course, because it's a minus to begin with, it stays as a minus. Now what we do is we take the diagonal products of each of these, stopping when we touch a row which we can integrate. This final row, plus 4 times minus 1/4, that's minus sine 2x. So we can integrate that row, so we're going to stop on this third row. So because this arrow is touching that third row, we don't do another diagonal arrow, we stop there, and then we're going to integrate this final underlined line. So from here, take the products like I said, and of course just bringing an arrow down here. That's going to be the integral of positive 2x squared times minus 1/2 cos 2x. That simplifies to minus x squared cos 2x. The next diagonal product, minus 4x times minus 1/4, that's going to give positive 1x, then sine 2x. So I'm just going to get plus x sine 2x. And then the integral of this. So positive 4 times minus 1/4, that's just going to be minus 1. So minus the integral of sine 2x with respect to x. Then of course we need to remember that sine actually integrates to negative cos. So the final step, I'm going to have minus x squared cos 2x plus x sine 2x, and then this here is going to become, because it goes to minus cos, we're going to get minus a minus, so we're going to get positive cos 2x, but of course because of that 2 we need to divide by that 2, so it becomes 1/2 cos 2x plus of course c. So that's f done. Integral g. So this time we've got sine to power 5 3x cos 3x dx. Now if you notice, the sines and the cos are both to the same variable. It's both in terms of 3x. So this is good. we don't need to think about splitting these up into different ones using compound or double angle formulae. So this isn't as bad as it looks. And what we need to always recall is the obvious, that sine differentiates to cos and cos differentiates to sine. And so the integral, sorry, the derivative rather of sine 3x appears here. It's cos 3x. So this is actually one of these types here. It's this here. So in our case, f of x is sine 3x, n is to the power 5, and f dash of x appears there. It's cos 3x. And so for this one, it's a u sub. So we're going to sub u is sine of 3x. So let's just write this down. So if I let u is sine 3x, differentiate with respect to x, that gives 3 cos 3x. So therefore, dx in terms of du, dx is going to be du all over 3 cos 3x. So therefore, this integral we're going to transform. So sine 5 3x cos x, sorry, cos 3x, forget everything sometimes, cos 3x dx, that can be transformed. And so the sine to the power 5 of 3x, we can call that u to the power 5. So we get u to the power 5, leave cos 3x as it is, and then dx is the same as du all over 3 cos 3x. So for dx, we've just switched here, and then we get a beautiful cancellation, which is what we wanted to happen. So cos 3x on the bottom will cancel with the cos 3x on the top. And so that will simplify very nicely now to just simply the 1/3 on the outside, u to the power 5 du on the inside. So integrate u to the power 5. That of course goes to u to the power 6 and divide by the new power of u. So I get 1/6 u to the 6 plus of course c. 1/3 of a sixth is 1/18. Put the initial variable back in. It wasn't in terms of u, it was in terms of x. So what is u in terms of x? It's sine 3x. So u to the power 6 is going to be sine to the power 6 of 3x. Then of course plus c. And that integral's done. Integral h is very, very similar, in fact almost the same question really as what was in the warm-up. So I guess now here's a chance to apply what we covered in the warm-up, questions 1 to 4. So I'm only going to show one way of doing it. If you want in more ways, just to see warm-up for the more ways to integrate the types of questions where it's sine kx, cos kx. In this case, k is 2. In the warm-up, k was 1. So just to recap, what we could do is a few things. So we could, as a warm-up said, we could do this by integration by parts, picking either u to be sine 2x or cos of 2x. Either would work. We could even use a substitution as well. So we could let u be sine 2x or u be cos 2x, because derivative of one looks like the derivative of the other. So yeah, there's a few different things, but my general preference is, if you have something which is trigonometric, to simplify the trig stuff first and foremost. And so the method I'm going to suggest is the trig identity. So this is my recommended method. Again, if you're thinking, well, can I do it different ways? As I'll say again, just check the warm-up questions. But because this is trig and we can simplify it, this is my preference first and foremost. So we need to recall the double angle formulas for sine. So sine 2 theta is the same as 2 lots of sine theta cos theta. So therefore, sine 2x cos 2x must be one the same as sine 4x. So sine 4x must be the same as 2 lots of sine 2x cos 2x. So that's what we're going to use. So this integral we can say is the same as, because sine 4x would be 2 lots of that, but we only got 1 lot. This is the same as only half of sine of 4x. Then sine actually integrates to a negative cosine. And so what this is going to give us now, we get the half, then we're going to get minus a quarter cos of 4x plus c. A half times minus a quarter is minus an eighth, so we get minus 1/8 cos of 4x plus c. And there are other answers if you picked different ways of doing this. So feel free to explore with Desmos and check the warm-up as I say, but my recommended method is this one here, using the trig identity. So that's my preferred way of doing integral h. Integral I. So again, we're told what to use now. We're told to use a substitution for u, let u be tan x. But of course, there's no actual tan x in this integral yet. So not only do we obviously have a method which is given to us, but we will need as well to use some trig identities. So it's this one because it's given, but also embedded within the method, we'll need to know some identities. So how does tan relate to sec to the power 4? Well, it doesn't exactly. But you should hopefully remember how tan relates to sec squared. The identity we need to be using here is that 1 plus tan squared of x is the same as sec squared of x. My very stupid and immature and potentially slightly inappropriate way of saying it is, if one person with an ego goes and gets themselves a tan, one person plus tan squared, they may well think they're sexy, sec squared. 1 plus tan squared, sexy. Whatever makes it stick in your head. So we're going to use this. And I'm going to rewrite sec to the power 4 as sec squared multiplied by sec squared. And by doing that, we can obviously then get in the tan squared somewhere. So here, of course, I can just say that this 1 plus tan squared, is the same as a sec squared. So I'm just going to replace one of the brackets, not both. So I'm going to leave that as sec squared here, then here, 1 plus tan squared x. So just switching out the sec squared with a 1 plus tan squared. As well as that, also, if u is tan x, what we'll need to do is also take du by dx. So just writing down to the side, if u is tan x, then we need to work out what du by dx is. And again, you have a formula book, so why not check it? Is this a standard result we're told, or a result we just need to know? Differentiating tan. Well, let's have a look here. These are integrals. So to differentiate tan, we're looking the other way around. So if sec squared integrates to tan, tan would differentiate to sec squared. There's no constant here, luckily, so normal tan just goes back to a simple sec squared. So differentiate tan, we get sec squared. So du by dx is going to be sec squared of x. And then from that, we can see that dx in terms of du is just going to be du multiplied by sec squared x. Dx equals, Sorry, I'm being a bit silly here. Can't do very basic maths. So yeah, rearranging this, my apologies, it's going to be du all over sec squared x. So I just box this off here. Then what we can do is replace this dx with du over sec squared. And so using the fact that dx is du over sec squared x, we can now go one further and get it in terms of du. And by doing that, again, the nice magic things happen. The sec squared will cancel. So if we do that now, just cancel off this sec squared here with a sec squared there, then we're going to have integral of 1 plus tan squared of x with respect to u. But of course, tan squared is u, so we can replace that. So we're going to have just the integral of 1 plus u squared with respect to u, because tan squared is u squared. This is now very, very straightforward. Couldn't be much simpler, really. So integrate 1, that gives us u. Integrate u squared will give us 1/3 u to the power 3, plus, of course, the constant of integration c. Final step, put the initial variable back in, which was x. If u was defined as being tan x, then this becomes tan x. 1/3 u cubed, of course, becomes 1/3 tan cubed x, plus the constant of integration, lest we forget. So that's integral I complete. Integral j, a free sine of a half x plus 1 dx. Well, which one of these methods do we have? Well, we've got sine of ax plus b essentially, and we can integrate sine of normal x. So this one is actually right here. It's a type f of ax plus b, where we can just sub u to be ax plus b. So therefore we're going to do this. So if I let u, I could just say u equals half x plus 1, but of course du by dx, differentiating this just gives us a half. So therefore dx, I can now multiply both sides by 2 and then multiply by dx as well. So I'm going to get that dx is going to equal 2 lots of du. So we can now use this and transform the integral to something much easier. So that's going to equal 3 lots of sine u, and dx, of course, becomes 2 lots of du. So all I've done here is, because that is u, I've replaced that with u, and dx becomes 2 lots of du based on this. So we can now just go ahead. So 3 times 2, of course, is 6. Can leave that inside the integral or take it to the outside. It doesn't particularly matter, it's just a constant. So then integrating sine of u with respect to u. Now, the sine of anything will integrate to actually negative cos. So that gives me minus 6 lots of cos u plus c. Put back in what u was. U, of course, is half x plus 1. So we get minus 6 lots of cos half x plus 1 plus c. And that's j done. K, we've got sine of 2x all over 3 plus cos of 2x cubed with respect to x. So let's just talk through the flowchart and see if we can gather what this one is. So just bear in mind what the actual integral is. So here we go, let's start here. There's no method suggested, so we go here. The integral is a fraction. So is it of this form? Is the denominator or a derivative of the inner function on the denominator, does that appear on the numerator? If f of x appears on the bottom, does this appear in the numerator? Let's just have another look. Well, the denominator is 3 plus cos 2x. If I differentiate cos 2x, I'd get minus sine 2x, which is the numerator multiplied by a constant term of minus 1. So actually, yes, it is one of these things here. Okay, so actually, this one I mean to say, where f of x is 3 plus cos of 2x. So we can make this substitution for u being f of x. So it's one of these types here we've identified. So we're going to use a u sub. So if u is 3 plus cos of 2x, then we can take the derivative, so du by dx, the 3 vanishes, it's just a constant. Cosine differentiates to negative sine, but because of that 2, we need to bring that 2 to the front. So we get minus 2 lots of sine 2x. Therefore, getting dx in terms of du, dx is just going to be du all divided by minus 2 sine 2x. So, using that, we can now transform this integral. So let's box all this off. Ready to be used pretty much now, to be fair. Because this integral is going to be, basically I'm going to leave the sine 2x as it is on the top. The bottom, because we've got 3 plus cos 2x, which we defined to be u, we can just replace that with u. So we've got u cubed on the bottom of a fraction. And then dx, in terms of du, we deduced was du all over minus 2 lots of sine 2x. So again, we can just add this in. So it's that times du all over minus 2 lots sine 2x. We can now neaten this up and cancel and go ahead and just actually do the integral. So of course that's sine 2x on the bottom, cancel with sine 2x on the top, which is pretty much exactly what we wanted to happen. So on the bottom now of this integral, we have a fraction with a minus 2. That of course means minus a half. So if I just factorise out the minus a half here, I'm integrating 1 over u cubed with respect to u, which of course is u to the minus 3 du. That'll give me negative a half. Increase the power by 1, then divide by that new power. U to the minus 3 therefore becomes u to the minus 2, and then divide by the minus 2. So divided by minus 2 is the same as multiplying by minus a half. Then of course we add on the constant of integration. So what we're going to have now is minus half times minus half gives a quarter. So get a quarter of 3 plus cos 2x to the power of minus 2 plus c. And that's integral to k dusted off. L, x over x squared plus 4 dx. I'm going to show you a sort of an emergency last-ditch move here, which I'm not going to recommend. But the most obvious thing I would suggest would be to realise this is a fraction, okay, and to spot as well that the derivative of the denominator, derivative of x squared plus 4, is 2x, which is identical to the numerator, just multiplied by some constant. So because of that, my suggestion would be to be using this result here. and subbing u to be f of x, where f of x is x squared plus 4. However, if you miss this, or under the pressure of an exam or whatever, you don't think to do that, there is also, like I mentioned earlier in the video, a trig identity, which we can always try for x squared plus 4. So I'm going to go here. I'm going to stress this is last resort. So don't be trying this as standard. This is just like an extra tool to have in your arsenal, just in case you need it. I've not taught this in previous years, so I'm trying it this year just as like a get out of jail card in case you're really, really stuck. It's just one more thing to try. So I'll mention that last, but first of all, the most obvious and safer way to do it is to spot that the derivative of the denominator sort of appears in the numerator. So we're going to set u to be x squared plus 4. From that, of course, we can take du by dx. So differentiate u with respect to x just gives us 2x. Therefore, dx in terms of du, dx is just going to be du all divided by 2x. So we can now transform this integral. So the top, pardon me, I'm going to leave as x. The bottom, x squared plus 4. Well, we said that is our u. It's going to leave that as u. And then dx is the same as du all over 2x. So just highlighting what I've changed here. I've just changed x squared plus 4 in terms of u. And we switched the dx in terms of du over 2x. And of course, now you can see that these x's will cancel, which is great. That's what we want. And so now we're just left with this fraction a half. And on the inside, we've just got the reciprocal of u, so 1 over u with respect to u. This is now a standard result we need to know off by heart, really. Integrating 1 over u with respect to u, or 1 over x with respect to x, integrates to the natural log of that denominator. So we're just going to get here a half of the natural log of the mod of u, plus, of course, c. Put back in what u actually was. U is x squared plus 4. Because x squared plus 4 is going to be positive for all real numbers, we don't need the mod symbols, but, you know, if in doubt, just leave them in anyway, I think is the best way, because you can't go wrong by doing that. So x squared plus 4, and of course, finally, the plus c for the constant of integration. So that's using the method of a u sub, spotting that the numerator is sort of the derivative of the denominator. Now, let's have a look at an alternative. Like I've said and mentioned in the warm-ups, if we see on the denominator x squared plus some square number, we can make a substitution for x being the square root of this, because adding a constant, we take the square root of that and substitute 2 square root of that tan theta. And so if we try x equaling 2 tan theta, then this can be transformed. Differentiate x with respect to theta. Again, this is a standard result. We need to know that tan differentiates to sec squared. So 2 lots of tan differentiates to 2 lots of sec squared theta. So therefore, dx is 2 sec squared theta d theta. So this integral, x over x squared plus 4 dx, that's going to become, leave the x as it is. The bottom, 2 lots of tan theta all squared gives 4 tan squared theta plus 4. And then dx, of course, is now 2 sec squared theta d theta. So just using the idea here that that's what dx is. And now what we can do here, in fact, yeah, silly, because I said x is 2 tan theta, I should really replace the x with a 2 tan theta there, because I can, so why not? So now, this enumerator, we can factorize out a 4. So, in fact, if we look here, we can simplify an awful lot eventually. So, anyhow, we're going to have 2 tan theta on the top. Underneath 4, we can factorize out, we get tan squared theta plus 1. And the top, 2 sec squared theta d theta. However, tan squared plus 1 is itself a trig identity. 1 plus tan squared is the same as sec squared. So now we can replace this with sec squared. And because we've got 2 and a 2 and a 4, we can essentially cancel this off. So 2 times 2 is 4. Dividing by the 4 just cancels nicely. So now we're just going to have tan on top. Bottom is going to be sec squared theta multiplied by sec squared theta d theta, which now nicely again cancels, because the tan squared plus 1 of course gives sec squared, and if I'm times it by sec squared but dividing here, again we can cancel off like so. So we simply have integral of tan theta with respect to theta. So again, is this a standard result we need to know, or are we told it? Check your formula book. Integral of tan goes to the natural log of sec of that angle. So it's going to be ln of sec theta plus c. ln, where we have mod sec theta of course plus c, but then putting back what theta actually was, well, we said x is 2 tan theta. Okay, so from this we can work out that theta, divide both sides by 2, I get x over 2 is tan theta, so then theta is going to be tan minus 1, or arctan of x over 2. So then we have ln of sec of tan minus 1 x over 2 plus c. It's been careful with my brackets there. There's an awful lot of brackets. As I say, and can't stress enough, this is a last-ditch effort. This is just if you're really not sure what on earth to do, just bear in mind this substitution for x being 2 tan theta is always worth trying. You've got x squared plus some square constant on a denominator. Almost always, in fact, possibly always, literally always, will be a different way of doing this. But if in doubt, if for whatever reason you're really stuck, this is just another sort of tool in your arsenal to try if you're stuck. So 2 ways, I'm highlighting different colours. For red is recommended. And as I say, the weird substitution of tan theta is an absolute last resort. But I wanted to show you it just in case, so it might be useful if you get yourself really, really stuck. Okay, integral of cos squared. So there's no real point, I think, in using the flowchart. I think it's obviously going to be a trig identity because it's just all trig. And cos squared isn't given to you in the formula book. You're not told how to integrate this. And so what we do need to do is to remember the double angle formulae. So I could do with rewriting cos squared in terms of something else which isn't hasn't got a squared thing in it. So if I just think about what cos squared is as a double angle, with a double angle formula, the links to cos squared x is actually cos 2x. So just remember, cos 2x is the same as cos squared minus sine squared. And then we can rearrange this. And so cos squared x, we can write sine squared in terms of cos squared x. So if I just leave cos squared obviously as it is, if I do minus sine squared, and sine squared of course is 1 minus cos squared of x, then we can see minus and minus cos squared is a plus cos squared, so we get 2 cos squared of x minus 1. So therefore, rearranging, cos squared of 2x is 1 and the same as cos 2x add 1, and then divide by this 2. So this is the take-home point we need to be using. So based on this, we can now integrate what we need fairly straightforwardly. So therefore, that integral is the same as the integral of cos 2x plus 1 all over 2 with respect to x. So I could, if I wanted to, factorise out the half or leave the half within the integral. It's entirely up to you, whichever way you want to do it. I'm sort of in the habit of taking out the fractions and constants now, so if I just take out that half, cos 2x plus 1 dx. So now we can just go ahead and integrate. And so the 1, of course, just integrate to x, so we have half x. Cos integrates to positive sine. So we get a sine x here, but because of this half, we need to also divide by this constant 2. So it's plus a half sine x in those brackets. Then, of course, plus c. Half multiplied by x, of course, is half x. Half of a half sine x is a quarter sine x plus c. And that's all we need to do for that one. So integral m has been integrated. Integral n. So it's a product. It's x cubed multiplied by the root of 5 minus x squared with respect to x. So I'll show you the flowchart for this one, the decision map. So if we start at the top, it doesn't suggest a method, this question. So go down this red arrow for no. It's not a fraction, so no. Is it of this form here, for example, a reverse chain rule, or can we use a simple substitution where one product looks like the derivative of the other? Well, no, not at all, to be honest. X cubed differentiates to 3x squared. We've got an x squared there, I suppose you could say, but this is all square rooted, so it's not that simple. And likewise, x squared differentiates to 2x, which is nothing like x cubed, so it's not a simple type of substitution like the one you might be used to. So no. Integration by parts. Well, we can integrate by parts when we have a product of two things, which is what this is. However, in order to use integration by parts, we need to be able to differentiate one of the products at least a couple of times or so normally, and to integrate the other easily enough. And again, if we look here, we can differentiate or integrate x cubed, but this one here, differentiating or integrating the square root of 5 minus x squared, again, isn't straightforward. So again, it's not obviously an integration by parts one either. So again, no. This is one of the reasons I included this example. What if you're really not sure what to do? So again, double check and rethink any useful trig identities. There's no trig in there, so skip that. Use substitutions. Can any product or group be written in terms of another? And often, if you're not sure what to do, it'll often be a use substitution. In this case, we can. So ignoring the square root for a second, just looking at the algebra, if I were to make a use substitution for calling u 5 minus x squared. And like I've mentioned in other videos, you'd normally pick u to be the more awkward looking thing. So this is more awkward than x cubed. If I picked u to be 5 minus x squared, I could make x a subject and then rearrange to get x cubed. So it's actually going to be an alternative substitution. So if it is algebraic and looks really awkward, one of the last resorts is to try u substitution and pick u to be the more awkward looking thing, essentially. So let's have a start. So I'm going to call u 5 minus x squared. So let's set it all out. So if u is 5 minus x squared, obviously du by dx, that's going to be just minus 2x because the 5 disappears. So therefore, writing dx in terms of du, we can see that dx is just going to be du all divided by minus 2x. And then afterwards, we can write the x squared in terms of u as well, because when we're dividing by this minus 2x, this will make the x cubed go down to x squared. So we'll see how this interval is going to be transformed. So we've got x cubed square root of u, this is, so I'm going to call that u to the power of 1/2, where u is 5 minus x squared. And then it's with respect to obviously dx, but dx we've just seen can be written in terms of du as du all over minus 2x. So let's just add this in as well. And like I said, by doing that, we can cancel off one of these x's on the bottom of this fraction here, and one of these x cubes. So I can call it x squared. So then, x squared, and then we'll take out this minus 1/2 as well, because that's just a constant term. So I've got minus 1/2, that's just going to be x squared u to the 1/2 du. But if this is what u is, which is what we defined it to be, 5 minus x squared, we can make x squared the subject and say x squared, therefore, if I add x squared to both sides and then take away u, x squared must just be 5 minus u. So the next step is we can switch x squared for 5 minus u. Of course, when you get confident, you can skip some of these steps or do multiple steps in one move. I'm just showing it step by step, so hopefully it makes it clearer what I'm doing and why. So again, all done here is just to replace the x squared with 5 minus u, because that is what it is in terms of u. Now we've just got a essentially a polynomial integral, which is quite straightforward. So if we expand out what's in this integral, so I've got 5u to the 1/2, then minus u times u to the 1/2 is u to the 3/2. All of that, of course, with respect to u. Give myself some more space, so I'm going to have minus 1/2, 5u to the 1/2, so the 1/2 is going to become 3/2, so u to the 3/2. I then divide by that new power. So dividing by 3/2 is the same as timesing by 2/3. 5 times 2/3 is 10/3. So I get 10/3 u to the power 3/2. And this one here, the 3/2, increase the power by 1, that's going to become 5/2. And divide by the new power. So dividing by 5/2 is the same as multiplying by 2/5. And of course, plus c. So I can do two things here. I can expand this out, and then what I can also do is replace what u is in place of x. So let's do the positive term first. So minus 1/2 times minus 2/5, this will end up being positive. So minus times a minus is a plus. 1/2 of 2/5 gives us 1/5 of what u is. So 5 minus x squared all to the power 5 over 2. Then minus a half times 10 over 3, that's going to become minus 5 over 3. U, which again is 5 minus x squared. That's to the power 3 over 2. And then plus c. And that's integral n sorted. Integral O. So this one's 2x all over 2x plus 1 with respect to x. I've included this one because it's a bit of a revision. Well, I suppose it all is, of course, maybe a silly thing to say, but it's revision of how to differentiate something of the form a to the power x, which is worth remembering in its own right. So again, just let's consider that. Once we know how to do that, the method will become obvious. I'm hoping by inspection you'll have an idea of what one it might be. In fact, change my mind. I'll just show you which one it's going to be. Essentially, you need to have in mind that differentiating exponentials is a weird thing. You always get something that looks like itself back. So if I were to differentiate 2x plus 1, of course the 1 will vanish. But the derivative of 2 to the x is basically some constant multiplied by 2 to the x. The derivative of this is going to be 2 to the x multiplied by ln2. So actually this one, though not quite as obvious, is an integral of this form. But I'm going to explain as well how we can show and remember that the derivative of 2x plus 1 is 2 to the x ln2. So let's just establish this and then we can move forward from that point. So if I just get this here, just put it in the box just as a reminder. So just imagine, let y, let's say, equal, let's go for 2x. I can take natural logs of both sides. So ln of y will be the same as ln of 2 to the x. And then if we're doing the natural log, one of the laws of logs is we can bring that power to the front. So that's the same as x multiplied by ln2. So then if we take dy by dx on both sides, so we can isolate and get what the derivative is, we need to use implicit differentiation here. ln x would differentiate to 1 over x. Therefore ln y differentiates to 1 over y. And then you always just stick on the dy by dx on the end. So it works like the chain rule, essentially. Differentiating x ln2, ln2 is just a constant number. So the x will vanish, and we just get ln2. Then if I multiply through by y on both sides, dy by dx is going to be y times ln2. But of course, what was y? Y was 2 to the x. So we get 2 to the x ln2. So that's worth remembering. So if y is 2 to the x, then dy by dx gives us 2 to the x ln2. So if we imagine this one here in this following way, so if I've got 2x plus 1 on the bottom of a fraction, if the top was 2 to the x ln2, that would be a case of the numerator is the exact derivative of the denominator, but of course there's no ln2 there. But what I could do is just balance this back out again by dividing by ln2 outside of a fraction, so outside of the integral. Like so. So now it's 1 over ln2, and now because we wrote this so that the numerator is the exact derivative of the denominator, that's just the same as ln of, oh, silly me, sorry, it's not 2 x, is it? It's 2 to the power x, I mean to say. Silly me, sorry. So I have 1 over ln2, then it's the natural log of 2 to the x plus 1 plus, of course, the constant of integration. And that's all we need to do. Integral p, we're told what to do. It's a u sub. We need to say u is root x. So the method's provided. We know the integral type. So let's just go through the motions. So we know that u is root x, so write that down. And then we need to find du by dx. So moving forward, the derivative du by dx. If I just actually think about root x as being x to the 1/2, it just makes it, I think, much easier to differentiate. Think of it in index form. So think of it as x to the half. The half comes to the front, so we get half. Then we take one from the power, so 1 less than a half is, of course, minus 1/2, which we can write as 1 over 2 x to the positive half, which is just 2 root x, but u is root x, so that's just the same as 1 over 2u. And from there, we can therefore work out what dx is in terms of du. So if du by dx is 1 over 2u, that's the same as saying that dx has to be equal to 2u du. And just use the fact that root x is, of course, u. So now we can transform the integral and proceed. So all this here is the same as 2 all over root x. Well, root x, we've established, of course, is what we called u. If root x is u, x must be u squared, and minus 4, of course, we can just leave as minus 4. And then dx, we can replace 2. So x minus 4 just becomes u squared minus 4. And the dx is the same as 2u du. And again, as almost always, you should be aiming and looking for some cancellations with these u subs. In this case, we can cancel the u on the top and the bottom of this fraction. So u cancels here and there. And now what we just have is 2 times 2, which is 4 on top. On the bottom, u squared minus 4 du. And that, of course, will now factorise, because this is a difference of 2 squares. So now what we're going to have is, on the denominator, u plus 2, brackets, u minus 2. And so then, actually, embedded within, my suggestion here would be to now use partial fractions. So step 1 and step 2, we're now going to use partial fractions. So now use partial fractions to proceed from this point. So now I'm going to say let 4 over u plus 2 u minus 2 equals sum a all over u plus 2 plus sum b, we're going to find, over u minus 2. Then in the same way with partial fractions, now what we're going to do is just multiply both bits by u plus 2 and u minus 2 to work out what a and b are individually. So multiplying both sides by u plus 2, u minus 2 gives us that 4 must equal a multiplied by u minus 2, because u plus 2 bracket will cancel. And in the same way with the b brackets, the u minus 2 will cancel, leaving us b multiplied by u plus 2. Now we can just pick different values for u. So when u is 2, we get 4. 2 minus 2 cancels. We're going to get b times 2 plus 2, which is 4. So 4 equals 4b, therefore b equals 1. Then to make this b vanish, we can now select u to be equal to minus 2, which then gives us 4. This bracket now cancels, and we get a minus 2 minus another 2, which is minus 4. So 4 equals minus 4 lots of a, therefore a equals minus 1. Piecing all this together, if I just call this integral now, I don't know, say I, it's letter p, but call it integral I. So therefore I, the actual integral, is just going to be a, which of course now is minus 1, over u plus 2, plus b, which is 1, all over u minus 2. All of that with respect to u. This is now going to be in terms of natural logs. The derivative of u is just 1. Because it's a minus 1, need to factorise out this minus 1 factor here. So that then gives us minus ln mod of u plus 2 plus ln mod u minus 2 plus c. We can now use the laws of logs. This is one log, essentially minus another log. The logs are to the same base, both natural logs. So we can say this is the same as ln of u minus 2 divided by u plus 2 plus c. Final step, go back and fill in what the actual original variable was. It was in terms of x, and u was defined as being root x. So we have on top root x minus 2, on the bottom of the fraction root x plus 2, all modded, plus the constant of integration. Now that constant as well, if I wanted to, I could have turned that constant ln k, and calling that ln k would allow me to put the constant within the natural log. So depending on how the question wants you to write the answer, this might be valid. Another form might be to write c in terms of ln of some other constant. They can combine this into just one single natural log. But assuming that's not an issue, that's our final answer for integral p. Integral q, x e to the x dx. So let's look at the flowchart again, if we want to. So no method suggested. It's not a fraction. It's not a case of reverse chain rule or one product being the derivative of the other, because e to the x is nothing like x when it differentiates, similar for differentiating or integrating x. Integration by parts we can use if it's a product. It is a product, it's x multiplied by e to the x, and we can differentiate x or integrate it, and we can easily differentiate and integrate e to the x. For that reason, we can use and should use integration by parts. So I use the DI method, which you'll probably know by now if you've had me as a teacher for a while with integration. So D we prioritize first of all as logs, and then algebraic in the absence of any logs. There's no logarithms, but x is algebraic, so we have to prioritize x for the D column, therefore in the I column goes e to the x. We differentiate the D column, so x goes to 1, 1 goes to 0. E to the x integrates to itself, to itself, to itself forever. Using this method, we take the diagonal products of each of the D and I columns, stopping when we get to an arrowhead which touches a line which we can integrate. The product of this line is just minus 1 times e to the x. Minus e to the x we can integrate, so we're going to stop at that line, because this line we can integrate. Therefore, we only take one diagonal product, because the arrowhead of this arrow here is hitting this line, which we can integrate. So therefore, all we need to do, based off this, and obviously this is our integral, we're going to have x times e to the x, that diagonal product, and then we're going to integrate minus 1 multiplied by e to the x, which is just minus e to the x dx. So x e to the x stays as is, minus e to the x integrates to its exact same self, then of course plus c, the constant of integration, to finish the job. And then we're done. Integral r. So we've got 4x plus 1 all over 2x squared plus x minus 1 with respect to x. Now, this one here, there's two main ways of doing this. One's very straightforward, the other is unnecessarily hard. So by far and out, the best way of approaching this is to just double check the derivative of the denominator. So this one here, differentiate 2x squared plus x minus 1 gives 4x plus 1, which is exactly what we have on the top. So the recommended suggestion, I would say, would be to go for this one here, where it's just simply f dashed of x over f of x to the power of 1 in this case. So this is recommended for sure. So all we need to do now is just say u is 2x squared plus x minus 1. So if u is 2x squared plus x minus 1, then du by dx will just of course be 4x plus 1. So therefore, getting dx in terms of du, dx will just simply be du all over 4x plus 1. So this integral therefore will transform into this. So what we're going to have here is 4x plus 1 on top. On the bottom, we said that was u, because we let u be this polynomial. I'll get a yellow colour for yellow. And then we saw that dx was du over 4x plus 1, which gives us a very nice and useful cancellation on the top here and the bottom there. So in other words, all we have to do is to integrate 1 over u with respect to u, which of course is the natural log of the mod of u plus c, and u of course is and was 2x squared plus x minus 1 plus c. Now there is another way of doing this, which would be to realise, this is really going the awkward way around, this denominator would factorise, of course. So what we could have done is actually factorised this denominator. So we could have actually done partial fractions here, but not at all recommended. So I'm just going to tick here, partial fractions could be done, definitely not recommended. This might beg the question, so why am I showing it you? It's, again, like I've said before, the more sort of tools you have in the toolbox to use in case one fails or you forget one of them, it just gives you another way of tackling a problem. Tackling it in a fairly awkward way, but being able to solve it is better than not being able to tackle it at all. So, how would this work if it's partial fractions? Well, step by step. First of all, we need to factorise this denominator. I'm not showing it step by step writing it because it's just so long-winded. So we take the fraction, factorise the denominator, like I say, and then split into two separate fractions. Now we multiply both sides of this by the denominator, which gives us that 4x plus 1 must be a multiplied by x plus 1 plus b multiplied by 2x minus 1. We can now try different values for x to eliminate a and b. So first of all, if I pick x is minus 1 to eliminate that bracket, 4x plus 1 becomes minus 3. Over here, that bracket's vanished. we get b multiplied by minus 2 minus another 1, minus 3. So if minus 3 equals minus 3b, the coefficient on this fraction at the top must just be 1. In the same way now, if I pick x to be equal to 1/2 to make this bracket disappear, then 4x plus 1 becomes 3, and x plus 1 becomes 3 over 2. So we get the equation 3 equals 3/2 of a. That can only be true if a is 2. Piecing this together now we know that a is 2 and b is 1. 4x plus 1 all over 2x squared plus x minus 1 could be considered as these two separate fractions to be integrated separately. So if you notice here, the derivative of 2x minus 1 is exactly the numerator. Same here for this fraction. The derivative of x plus 1 is 1. So to integrate this, it's just the natural log of this denominator plus the natural log of the mod of this denominator plus, of course, the constant of integration, which is c. And then just to go a bit further, in brackets, using the laws of logs, log of one plus log of another is the same as log of these two things combined as a product, like so. And then, of course, the mod of these two brackets expanded will be the same as the mod of these two brackets factorised. So to go full circle and to get us back to this, if I were to expand this out, we get 2x squared plus x minus 1 plus c as required again, but I'm hoping you can see very, very clearly. One way is very straightforward, the other way is very time consuming. So the lesson in its own sense is to practice, 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 so you get comfortable and more familiar spotting which is the most efficient way of tackling each integral. Integral s. So this time we've got 2x plus 1 on the top, and the bottom is square root of x squared plus x plus 5 dx. So this is a fraction. So let's have a look what the flowchart says. No method suggested. It is a fraction. So let's go to this root here. Is your integral of this form, where we've got a function on the bottom, perhaps to some power, and on the top, the derivative of that inner function? Well, the answer is yes, we do. The inner function here on the denominator is x squared plus x plus 5. The power can be considered as a half, because it's being square rooted. But the inner function, x squared plus x plus 5, the derivative of that is 2x plus 1, which is exactly the numerator. So actually, yes, what we can do here is to use a u substitution because it's of type 2 here. My bad, type 3. It's one of these. So for that reason, we can use a u sub. So I'm going to go for this. So let u equal x squared plus x plus 5. Then we can take du by dx. Du by dx is just 2x plus 1. Therefore, dx in terms of du, dx is going to be du all divided by 2x plus 1. So now we can change this integral. So this is going to equal, obviously, 2x plus 1 on the top. This here, because that's u, this is just the square root of u, is what we're taking. So we've got u to the power of a half on the denominator. And then dx is the same as du all over 2x plus 1. Next, we can proceed by cancelling. So the 2x plus 1 here cancels with 2x plus 1 under there. And so because we've got 1 over u to the because we've got 1 over u to the positive half, that's the same as me saying it's u to the negative 1/2 integrated with respect to u. Now this here, we're integrating a simple function of u, so we just increase the power by 1. So add 1 to a half gives us u to the half, and we need to divide by that new power. Dividing by a half is the same as multiplying by 2. So we're going to get 2u to the 1/2 plus c. However, u is x squared plus x plus 5, so we can put this back in. And we can put it as a power half, or we can put it as a square root. It doesn't particularly matter unless the examiner specifies. I'm going to put it as a power. So I've got x squared plus x plus 5, that to the power of 1/2 plus c. And that's all we need to do for integral s. Integral t. So this time we have a algebraic product. We've got x multiplied by x minus 2 to the power 7. So in my mind, at least, it's a product of two separate things. I suppose you could think of it as a product of 8 things with 7 brackets and an x, but essentially this is a product of 2 different entities. So this could be an integration by parts if we can integrate one and differentiate the other. Now x minus 2 to the power 7, that's just a function of that's just a linear function of x. So it's linear in x minus 2, just powered up. So that's easy enough to integrate. You can just think of u being x minus 2. In the same way, you can very, very easily differentiate x. So the preferred way of doing it, in my opinion, is to use differentiation by parts. Sorry, integration by parts. What's wrong with me today? So let's do it this way. Although, because we can easily write one of these things in terms of the other, we can also do this as an alternative type of u substitution. So I'll show both ways. We'll have different looking answers, which you can then check with using Desmos after to show that they are completely equivalent to one another. So, first of all, how to do this. So, if I just move forward, actually that's probably easier. So, if we do this first of all by parts, remember we need to prioritize D as whatever is in the, according to LATE, whichever comes first out of log, algebraic, trig, or exponential. Well, both are algebraic, so we're just going to pick whichever one's easy to differentiate. I'd much sooner differentiate x than x minus 2 to the power 7. So let's go to differentiate the x. Differentiating x, dead easy, goes to 1. Differentiate 1, we get 0. Therefore, we need to integrate the x minus 2 to the power 7. Now, this step, I'm not going to go into any great detail with it. If you want to refresh your memory, I'd suggest to go back to 11.1 and 11.2. This here, to integrate this, treat it as just a normal x. It works in the same way because there's no coefficient and it's not an x squared. So we'd raise the power by 1 and divide by the new power. The integral of this, therefore, is just 1/8 x minus 2 to the power 8. And we stop with this DI method. When we get to a row, we can integrate the product of. Minus 1 multiplied by this, we can integrate that fairly straightforwardly. So we're going to stop at that row. So I'm going to underline that. And we take the diagonal product of all the rows until we get to an arrowhead which touches the final row, which is just the first arrow. Because this arrowhead here is on the final row. So all we need to do here is take this diagonal product. So the integral, therefore, of x minus 2 to the power 7 dx, that's going to be 1/8 of an x multiplied by x minus 2 to the power 8. So that's the first thing we're going to do. So 1/8 x minus 2 to the power 8. And then we're going to take the integral of this product. So it's going to be minus 1 times this, all integrated. So it's going to be minus the integral of 1/8 x minus 2 to the power 8 dx. So we'll leave this one as it is. Of course, yeah, we're going to get the plus in a second. So we get 1/8 of an x minus 2 to the power 8. Integrating this power of 8 will go up to a 9, then we divide by that new 9. So 1/8, then a 9th of that will be 1/72. Dividing by 8 and dividing by 9 the same as divided by 72. The power 8, as I say, has increased to the power of 9. And then we just have plus c. And so that's using by parts. We could also have used a u substitution. So, because we can write x in terms of x minus 2, and x minus 2 is a more awkward thing, let's pick u to be x minus 2. So we'll let u be x minus 2. Therefore, du by dx just gives us 1. So therefore, du is exactly one and the same thing as dx. So therefore, this integral x minus 2 to the 7 with respect to x is one and the same. Well, x, because u is x minus 2, I can work out, of course, so x is going to be u plus 2. So the first thing I'm going to switch is, because x is u plus 2, it's going to put that in place of x. So I get u plus 2. And then the x minus 2 is u, so that just becomes u to the power 7. And then du is the same thing as dx. So u is x minus 2, so x minus 2 to the power 7 just becomes u to the power 7. X, like I said, is u plus 2, so just colour coding where each thing's come from, and dx is the same as du. So now we can expand this out and integrate. So expand out of this bracket. U multiplied by u to the 7 is going to give me u to the power 8. And 2 times u to the 7, of course, is going to be 2u to the 7. All with respect to u. So u to the power 8, that will integrate to 1/9 u to the 9. 2u to the power 7 will integrate to 2u to the power 8, all divided by 8. But 2 divided by 8, 2/8 is the same as a quarter. So get 1/4 u to the 8th plus c. And the final step, put it back in terms of what u actually was. U is x minus 2. So I get 1/9 x minus 2 to the power 9 plus a quarter of x minus 2 to the power 8 plus c. So whichever your preference, the answers look different, but you can verify these using Desmos. These are equivalent forms. Okay, integral u. So we've got a product of two different things, both are trigonometric. So cosec squared 2x, cot 2x with respect to x. So if this is looking fairly unfamiliar to you, which is absolutely fine, my first suggestion would always be to just check the formula book to see if it's a simple identity which we're given we can integrate. So is there anything which just tells us how to integrate cosec squared cot 2x? So if we look here, these are all listed as integrals, so this is just a combination of what it gives you in the formula book for derivatives and integrals. I'll just put them all in terms of integrals essentially. So what did we have? It was cosec squared cot. Both are in the form of 2x. So do we have cosec squared cot? No, we have cosec without cosec squared. That's not quite what we need. So essentially we're not given it. But are we told the derivatives of either cosec squared or cot? Well, let's have a look. And remember, we can use this form here if one of these derivatives appears as the other one of these products. So what's the derivative of cosec squared 2x? So because these are all integrals, I'm looking the other way around. Are we given cosec squared anywhere? No, we're not. Are we given the other one, which I believe is cot? We're told what cot differentiates to. So I'm looking for cot here. Oh, here we go. So minus cot differentiate to cosec squared. So we can take this and adapt it essentially. So based on this here, cot will differentiate to negative cosec squared. And so that's what we're going to use. And because cosec squared appears here, then it is indeed actually the reverse chain rule. It's this type here. So we're going to use f of x being cot 2x. So let u equal cot 2x. Then, this is from the formula book, like I've just shown you. Differentiate du by dx. Cot differentiates to cosec squared. But because of this 2 term, slightly different to minus cosec squared, like I said. So we get a minus 2, because of that 2 here. Cosec squared, again, it's going to be a 2x. So therefore, dx in terms of du, dx is just simply going to be du all over minus 2 cosec squared 2x. So this here is going to become cosec squared 2x. I'm just leaving that exactly as it appears. Cot 2x, which we said is just u, and then dx, which we've established is du all over minus 2 lots of cosec squared 2x. So now we can just go forward really. So we've let that be cot 2x, which is our u, and then we worked out that dx is du over minus 2 cosec squared 2x, which is pretty great, to be honest, because the cosec squared on the bottom, we can cancel the cosec squared there. And so if I take out this factor of minus a half as well, and just put this to the outside, that's not the colour I wanted, we can have minus a half integral of, that's just going to be u with respect to u, so it's going to be u du. Integrate u with respect to u, dead easy. The power is going to become 2, divided by the new power, so it becomes half u squared. And then, of course, remembering the constant of integration. So, minus a half times a half is a quarter, well, minus a quarter. U, of course, was cot 2x, so u squared is cot 2x squared, which we write as being cot squared of 2x, with the notation. And of course, just for plus c at the end to finish off. Therefore, the integral is negative a quarter of cot squared 2x plus c. Integral v, it seems so obviously partial fractions, I'm not even going to show you the flowchart, to be honest. The only other thing it could honestly be is to check if you expand this out, you'll get something to do with x squared. Does that differentiate to 2x minus 6? Well, it doesn't. The x squared you get does differentiate to 2x. But if you expand this out here, you don't end up with minus 6x. So it's not going to work. So it's going to have to be partial fractions. So straight away, you should be fairly familiar with this if you've done the partial fractions chapter. So assuming you have, of course you should have done. I'm just going to split this into 2 separate fractions, with one denominator being a over one of the denominators, and the other numerator being b over the other denominator, x minus 1. Then imagining multiplying, I should really say that differently, so hold on, my bad. It's not the integral, it's the fraction I'm doing first. So let's be technically correct. Sorry to do this, bit of a squeeze. So anyway, if I multiply both sides now by x plus 3, x minus 1, we then see that 2x minus 6 would have to be a multiplied by x minus 1 plus b multiplied by x plus 3. We can now choose different values for x to eliminate one bracket, focus on the other. So first of all, if I go for x equaling 1, so if x equals 1, 2x minus 6, that'll just become minus 4. The a bracket will vanish because 1 minus 1 is 0. 0 times a is nothing. And over here, b multiplied by 1 plus 3, which means 4b. So therefore, b equals minus 1. Next, I'm going to pick x to be negative 3. So if x is negative 3, minus 2x is minus 6, minus another 6 gives minus 12. I then get the minus 12. This bracket will vanish like I've said. Over here, minus 3 minus 1 is minus 4 times a. Dividing through by minus 4 on both sides, minus 12 divided by minus 4 gives positive 3. So therefore a equals 3. I'll just call that I for a second. So therefore the integral I is going to equal a, which is 3 over x plus 3, plus b, which worked out was minus 1. In fact, so I'll put a minus there. What am I doing? And minus 1 over x minus 1 with respect to x. So now what we can do is realise, I'm hoping we realise, this is going to be in terms of natural logs, because the derivatives of the denominators appear on the numerators, multiplied of course by a constant in some cases. The derivative of x plus 3 is just 1. The numerator is 3 times bigger than 1, so this is going to integrate to 3 lots of the natural log of mod of x plus 3. Then over here, I'm minusing off, well, the derivative of x minus 1 is exactly 1. So this does integrate to just natural log of itself. Well, minus natural log of itself because of its negative sign. So I go minus ln x minus 1. Then, of course, plus c. This can now, though, be combined into a single logarithm. So, because it's 3 lots of ln x plus 3, I can take this as a x plus 3 cubed. So it's ln x plus 3 cubed minus ln x minus 1 plus c. Then finally, using another law of logs, log of one thing minus log of another, where the log is to the same base, which is here, it's both natural logs. That's the same as the log of one thing divided by log of the other. So finally, we can say it's natural log of x plus 3 cubed all over x minus 1 plus c. And as I've said before, with constants of integration, when it comes to logs, sometimes the examiner might want you to include some constant within the natural log. In that case, you'd rewrite c as ln of some other constant. Then you can use law of logs to combine both ln's into a single natural log. But for now, because the examiner's not told us what to do, we can leave it like that, and that should suffice. So that's the final answer for integral v. Integral w, again, is a product. It's algebraic, x, and the second product is trigonometric, sine of 2x plus 1. So again, I'll just show you the flowchart in case you need it. It doesn't suggest a method, this question. The integral is not a fraction, so is it of this form, where one of the products looks like the derivative of the other? Well, in this particular case, no, not really. So what we have got, though, is a case where we can use integration by parts, because one of the things we can differentiate a couple of times if needed, and the other bit we can integrate a couple of times if needed. For example, here I can differentiate the x, I can integrate the sine. So for that reason, we're going to go for integration by parts. My favourite method by far now is this DI table method I discovered. So we prioritise what goes in D first according to the acronym LATE. L is logs, nothing log here, so that's fine. Next is A for algebraic. A comes before T, and we have an A thing here for algebraic. So we prioritise the A algebraic x before the T trigonometric sine 2x plus 1. So because x comes first because it's algebraic, we put that in the D column first and foremost. Therefore, the I column has to be sine of 2x plus 1. We differentiate x to get 1, we can differentiate again to get 0. Sine 2x plus 1. This is a function of the type ax plus b. I'm not going to go into another lesson how to integrate sine of 2x plus 1, but it works very much like integrating sine of x, so long as we remember to divide through by this constant factor of 2. The derivative of sine is positive cos. Therefore, the integral of sine, it goes to negative cos. So we're going to get minus cos of 2x plus 1, but dividing through by this half, we get minus a half cosine 2x plus 1. We stop when we get to a row we can integrate. Could we integrate minus 1 times minus a half of cos? Yeah, we can. So that's our final row. We don't need to go any further. So I'm going to underline that, and then we take the diagonal product until we get to an arrowhead which hits the last row, which is this first diagonal arrow, because this arrowhead here rests upon the final row. So therefore, all we need to do is take that diagonal product. So we've got x multiplied by minus a half cos 2x plus 1. So that's just going to give us minus a half of an x cos 2x plus 1. So we're going to integrate this product. So minus 1 times minus half is positive 1/2, which I'll put on the outside of the integral. On the inside, just cos of 2x plus 1 with respect to x. Again, if you wanted to integrate it here, you could cos integrates to a positive sine. So we're going to get sine of 2x plus 1. But because it integrates to positive sine, the sign isn't going to change. But because of this constant factor of 2 again, I need to divide by 2 yet again. So the minus a half becomes minus a quarter. So now we can just go ahead and deal with all of this now. So that's going to give me minus a half of an x cos of 2x plus 1. And then here, because I was integrating a half of cos 2x plus 1, that's going to give me now, of course, because that minus half I've dealt with twice, so that's slightly confusing. So, because I factored out that half here, you see. So if I were just to integrate the cos 2x plus 1, that'll go to positive a half sine 2x plus 1. Plus, of course, c. We can slightly neaten this up a bit. So we get a half x cos of 2x plus 1 plus a quarter of sine 2x plus 1 plus, of course, c. And that's all we need to do. Integral x. So it looks like a fraction. You've got 12x on top, root of 4x minus 1 underneath. So again, the age-old question, what on earth are we going to do here? So I'll use the flowchart. So it looks like to be a fraction. No method suggested. It is a fraction. Is the integral of this form where we've got either the derivative of the denominator or the inner function of a denominator appearing upon the numerator? Well, no, not really. There's nothing like that at all. If you look here again, 4x differentiates to just 4, not anything to do with 12x. And 12x differentiates to 12, nothing like 4x minus 1. So it's not that simple. So I can't use that type of u substitution. So it's no. Is the numerator and denominator polynomial? And again, are they whole number powers? Well, we can't really use partial fractions here because, again, the powers aren't integers, they're not natural numbers. If I just scroll up, I'll explain what I mean. If this, for example, were 4x minus 1 squared and maybe another thing, we could maybe do partial fractions. But when it's just one thing here, square rooted, we definitely can't use partial fractions. Okay, so it's not partial fractions either. Okay. Is it a polynomial numerator and one that could be factorized? No, we can't do partial fractions or split it into a separate fraction. But if we come over here now, have we considered rewriting the fraction as a product? Well, no, we haven't. Let's do that and consider if we can use integration by parts. So let's just rewrite this as 12x brackets 4x minus 1. That's been square rooted, but it's on the denominator. So that's the same as to the power of minus a half, like this. So could that be an integration by parts? Could we differentiate one thing? Well, 12x, we can differentiate that easily. And with a bit of consideration, because this is just a function of ax plus b, it's a function of a linear function of x, we can integrate that with a bit of thought. That's not so bad. So yes, we can actually do integration by parts here. However, let's imagine that you didn't spot this could be written as a product. It's not that obvious to do when you're under the pressure of an exam. I'll also give you a second method. You may have spotted that I could fairly easily write 12x in terms of 4x minus 1 with some algebraic manipulation. So I could also do a u substitution. And so I'm just going to copy this here and I'll show you how we can use a u substitution as well as integration by parts. So just reminding what I had from before. I'll show you both ways. So by parts, we're going to differentiate 12x, which goes to 12, then to 0. Therefore, we're going to integrate this 4x minus 1 to the power minus 1/2. Now, when we integrate it, that power of minus a half, we're going to add 1 to it, so it's going to become positive 1/2. However, the 4x minus 1 itself will also end up being divided. So I'm just going to write 4x minus 1 here, because I need to divide by the new power, so I need to divide by a half, but because of this coefficient of 4, I also need to divide by 4. Dividing by a half is the same as multiplying by 2, and dividing by 4 is, well, dividing by 4. So timesing by 2, dividing by 4, that's the same as multiplying overall by 1/2. Again, I'm just doing this in one line in my head, so a bit more jotting. You should convince yourself, hopefully, for 4x minus 1 to the power minus half does integrate to a half of 4x minus 1 to the power of 1/2. We stop when we get to a line we can integrate the product of. If I do minus 12 multiplied by this, I'm going to get minus 6 lots of 4x minus 1 to the positive a half. We can integrate that, so we can stop here. And we take the diagonal product until we get an arrow that hits the final row. So we just need one diagonal product. So we're good to go. So 12x multiplied by a half is just 6x. So we get 6x lots of 4x minus 1 to the power of a half. And then we're going to take the integral of this product on the bottom. So minus 12 multiplied by a half is just minus 6. I'll write that on the outside of the integral. And on the inside, we're going to integrate 4x minus 1 to the positive a half with respect to x. So the first bit I can leave exactly as it is. We've got minus 6, put this in big squared brackets. So for 4x minus 1, we increase the power of that from a half to 3/2, add 1 to it. Then of course we divide by the new power. So we're going to divide by 1.5, but also this constant term 4. Dividing by 1.5 and dividing by 4 is the same as dividing by 1.5 multiplied by 4, which of course is 6. And then the 6 here will cancel the 6 on the outside, and just of course remember the constant of integration. Finally, just neating it all up, we get 6x, 4x minus 1 to the 1/2, then just minus 1 lot of 4x minus 1 to the 3/2 plus c. Whoops, didn't mean to just randomly put a red smudge. So I personally would have done it using integration by parts. The second method I'm going to show you now is an alternative substitution. So what I could have chose to do is to have wrote 4x minus 1 as u. So let's do that now. So let's allow u to be 4x minus 1. So from that, we can take du by dx, which of course is 4. So and therefore, rearranging that to get dx in terms of du, dx is just going to be du divided by 4. So the integral, we can start to transform it. So we have 12x all over the square root of 4x plus 1 dx. We can now rewrite that as the following. By the way, I've still got an x here as well, which is slightly annoying. I wonder if I could write this 12x in terms of u. Well, if I look here, I could get 4x in terms of u easily. Then once I've got 4x, I could triple it to get 12x. So just to the side here. If I add 1 to both sides and triple, I'm hoping I can convince you fairly easily to consider that 12x must be 3u plus 3. So because of that, I can now switch 12x with 3u plus 3. So that's the first thing I'm going to change. So I'm going to write 3u plus 3 here. And underneath is the square root of u, which I'm going to say is just u square rooted. And then here, dx is now du all over 4. So again, just colour coding in what we've done. 4x plus 1, that is u. And of course, dx, we've deduced, is du all over 4. So now we can proceed. So because we've got a quarter on the bottom of the fraction, we can just go forward and take that quarter to the outside. And now, because we've got a numerator and this denominator, I can split this into 2 separate fractions. So 3u divided by root u is going to be 3 lots of root u. I'm going to write it as u to the power of 1/2. And then the next thing we're going to do, so again, like I'm saying, the second part of this fraction, 3 divided by square root of u, I can say that is 3 lots of u to the negative 1/2. Like so. So now I can integrate these parts separately. You can get a quarter. U to the 1/2 integrates to u to the 3/2. Then need to divide by that new power. 3/2 is of course 1.5. So 3 divided by 1.5 just gives me 2. This one here, the new power of u is going to become positive 1/2. I then divide by that positive 1/2, which is the same as times in by 2. So 3 times 2 gives 6. I get 6u to the 1/2. Then of course plus c. So then I can simplify this somewhat. So I'm going to get 1/2 u to the 3/2. A quarter of 6 is 6 quarters, which is the same as 3/2. So I'm going to get 3/2 of u square rooted plus c. Finally, just switch out u in terms of x again. U is 4x minus 1. So get 1/2 of 4x minus 1 to the 3/2 plus 3/2 lots of 4x minus 1 to the 1/2. and then plus c. And so this result here looks different, quite a bit different to the first one, but they are equivalent, and if in doubt, do check on Desmos if you don't believe me, but this one is equivalent to that one. So either way you've done it, either solution should be absolutely fine. Integral y, again this looks like a fraction. We've got ln x on top and x cubed on the bottom, so again, use this flowchart if needed. So does it suggest a method regression? No, it doesn't. The integral is a fraction, yes, but it's not of one of these forms here. It's not of a form where the denominator looks anything like the derivative, sorry, the numerator looks anything like the derivative of the denominator. So it's nothing like this, so we can't use that type of use substitution. Both terms aren't polynomial. Look here, the denominator x cubed, that seems fine, but ln x, it's not going to be a case of splitting this into separate fractions, and definitely not partial fractions. That's not going to get us anywhere, because the top isn't algebraic, it's logarithmic. So let's go this way. Have we considered yet rewriting this fraction as a product? No, we've not, so let's try that. So it might be an integration by parts. So we can use this if we can differentiate one group and integrate the other. So let's just consider this now. So I can rewrite this as the integral of x to the minus 3 times ln x dx. Now I can use integration by parts, and the reason I can do this is because I can easily differentiate ln x, and a power of x is just very straightforward. I could do this from year 12 knowledge. So let's go integration by parts. We prioritise d, what we're going to differentiate, according to the acronym LATE, where L to begin with is logarithmic. We do have something logarithmic. We've got ln x, so because L comes first, we put d first in this column. So differentiating the natural log of x. Well, if we differentiate ln x, we need to remember we get 1 over x. The other column is what we're going to integrate. So we're going to integrate x to the minus 3. So if we integrate that, the power is going to increase by 1 to minus 2, and we divide by the new power. So we're going to divide by minus 2, so we take a fraction minus a half, like so. With the DI method, we stop when we get to a row we can integrate the product of. If I take the product of minus 1 over x and minus a half x to the minus 2, that's just going to give me minus a half x to the minus 3, which again I can definitely integrate. So we can stop there because we know how to integrate that final row. So we can park it there and stop. And what we do, we therefore take the diagonal products of all the other rows up to that one. So we're going to take the diagonal product of ln x and minus a half of an x squared. So when we do this, we'll be absolutely fine to proceed. So therefore, we're going to get minus a half ln x times x to the minus 2. And minus a half, I'll put it as x to the minus 2 first. ln x. Then we're going to take this integral here. So minus 1 over x times by minus a half, when it's been positive a half of x to the minus 2 multiplied by 1 over x gives x to the minus 3. So now we can go forward with this. So I've got minus ln x, or x now as, all over 2x squared. Just looks slightly better writing like this, I think. It's equivalent, it's no different. And then over here, I've got plus a half of the integral of x to the minus 3, which of course we did in this line anyway, so we can reuse what we did earlier. So that just goes to minus a half x to the minus 2. Of course, plus c. Final step, make it slightly neater. So we've got minus ln x over 2x squared, and then over here, half times minus half is minus a quarter, x to the minus 2, so I've got minus 1, x to the minus 2 of course is the same as over x squared, and finally plus c for the constant of integration. And that's integral y. Integral z. So x plus 1 multiplied by x squared plus 2x plus 3 to the power 4. I'm going to let you try the flowchart yourself, to be fair. Pause it now, and if you've not made your decision about what method to use, but it would actually be one of this type here. Oops, I'll use a different colour pen. So it's going to be this type. So you're going to make a substitution for u being x squared plus 2x plus 3. So that's what we're going to do. So we'll let u equal x squared plus 2x plus 3. Therefore, du by dx, x squared becomes 2x, and 2x becomes 2, which you can see as the same as x plus 1, just different by a factor of a half, which is why we can use this u sub method. Again, we need to work out what dx is in terms of du, so dx we can rewrite as du all over 2x plus 2. So the integral becomes, just writing out as it was, so x squared plus 2x plus 3 all to the power 4 dx. That's one and the same as x plus 1 u to the power 4 times du. Now what I'm going to do here, I'm going to factorise out a 2 from this denominator because it just makes it easy to see where we need to cancel by doing that. So all we've done here so far is just rewrote u in place of x squared plus 2x plus 3, and of course dx we saw is the same as du over 2x plus 2, which in factorised form is this here. And then we can see what we need to do in terms of cancelling. We cancel this x plus 1 with that x plus 1. Then moving forward, we've got this factor of a half, so you need to take that half to the outside. I could leave it on the inside, doesn't particularly matter. Then I'm just going to need to integrate u to the power 4 with respect to u, which is dead easy. So that just becomes a fifth of u to the 5. Whoops, what am I doing? Silly. That's the actual integral. Don't need to write the integral sign again. So it's that plus, of course, the constant of integration. So we've got 1/10 u to the 5 plus c. Then just put back what u was. So u was x squared plus 2x plus 3 to the power 4. Sorry, just x squared plus 2x plus 3, I mean to say. That's now to the power 5, so raise it up to that power. Of course, plus c. And that's integral z. Integral AA, so the 27th one. I want to give enough practice, maybe too much, yes. So we've got 4 over 2x plus 1 multiplied by 1 minus 2x. This is a fraction, and it's algebraic on top. X to the power 0, you can consider that 4x to the 0, and the bottom's definitely algebraic, so we can split this into partial fractions. So let's just rewrite this as sum a over the first denominator, the factor, plus sum b over the second factor of the denominator, which is 1 minus 2x. Therefore, if I multiply everything by 2x plus 1, 1 minus 2x, in fact, this is a bit annoying. I've done this before in this video. When I say that, I don't literally mean the integral is equal to that fraction. I mean what's inside of the integral, technically the integrand, is equal to this fraction. So to be technically correct, I need to write this a bit better, don't I? So what I mean to say, to be accurate, is 4 over 2x plus 1, 1 minus 2x, equals sum a over 2x plus 1, plus sum b over 1 minus 2x. Therefore, if I multiply by both of these terms, I see that 4 must equal sum a multiplied by 1 minus 2x plus b multiplied by 2x plus 1. Now I just pick different values of x to knock out each bracket in turn. So my first suggestion is I'm going to let x go for a half. So if x is a half, this bracket will be knocked away. So I get 4 equals b times 2 halves plus 1, which means 2 times b. So therefore, b must just be 2. Now, if I try maybe x to be negative a half to get rid of that bracket here, then I see that 4 must equal a times 1 minus 2 lots of minus a half. Minus 2 times minus half is plus 1. 1 plus 1 is 2. So 4 equals 2a. So therefore, again, in the same way, I get that a also equals 2. So with the integral, which I'm just going to call I out of laziness, it's going to be the integral of a, which is 2 all over 2x plus 1, plus b, which again was 2, all over 1 minus 2x with respect to x. This is now going to give us a result in terms of natural logarithms. The derivative of 2x plus 1 is 2, so this is set up perfectly. That'll just integrate to ln of the denominator. So I get ln mod 2x plus 1. This bit here, the derivative of 1 minus 2x will be minus 2, which is the same as 2 multiplied by minus 1. So this will integrate to minus 1 lots of the mod of the denominator. So I get minus 1 times ln of the denominator. Then I need to remember, of course, the plus c. Because these are both in terms of ln, I can combine these into a single log using the law of logs. ln of one thing minus ln another is the same as ln of one thing divided by the other. So my final step is to write 2x plus 1 all over 1 minus 2x, close brackets, plus c. And that's double A. Double done. The last one, the 28th out of 28, integral of cos x to the times e to the sine x to the power 4. Well, this is a bit of a trick question, and this could be wrote much simpler. So I'm just going to rewrite this as cos x, and because I've got a power next to a power, I can just call that e to the power of 4 sine x, if I wanted to. So now what I'm going to do is I'm going to suggest that we make a u substitution, because the sine x differentiates to cos x. Okay, so here this is of the type k f dash x g of f of x to some power. So f of x is sine x, g is e to the x, so g of f of x is e to the power of sine x, all to the power 4. So just knowing what substitution to make is the hardest thing, but once we know what to do, it's going to become very simple indeed. But again, with these types of substitutions, the key spot is that one thing in this product looks like the derivative of the other. Sine x differentiates to cos x. So let's try that. We're going to go for u to be sine x. Okay, so du by dx is just going to be cos x. So therefore, rearranging, dx must be du all over cos x. So now we can begin to transform this. So the integral cos x e to the sine x to the power 4 becomes cos x e to the sine x, I'm just going to write as e to the u to the power 4. Oh, I've messed the dx off, silly me. And dx, of course, is du all over cos x. So again, just piecing this together. So we said let u be sine x, and of course dx was du all over cos x. That now enables us to cancel the cos x away. So that cos x here cancels with cos x over here. So now I'm just going to get e to the power u to the power 4, which simplifies, like I said earlier, over here. That's the same as e to the 4u du. Now, when we integrate in terms of powers of e, the power stays locked. So the power is not going to increase by 1 this time. So it's still going to be in terms of e to the 4u. However, because we have a constant before the u, we need to divide by that constant. So it becomes a quarter of e to the 4u plus c. Just remembering to put u back in terms of x. 4u must mean 4 lots of sine x. So I've got e to the power 4 sine x plus c. And that's all of them. So thank you for watching some or all of that. I imagine just some. I don't think you'd watch it all. I hope that's been useful practice for you to get used to knowing what to do with integrals before knowing how to then tackle them second. Please do leave a comment if you need any more help, or seek me out in school if you're still not sure. And please just never give up with maths. Any improvements can be made, even if improvements are very, very slow, bordering on being imperceptible. If you do more, you will get better slowly but surely. As I say, thank you very much for listening. I'll stop now. Take care, and I hope to see you all very soon. The end.